Okay. So today's session, we're going to finish chapter 14, ending with electrocyclic reactions, and then move on to chapter 15 on benzenes, aromatic rings, and then the EDGs, EWGs, activators, deactivators, and then do some Kahoot problems on that. I don't have like a lot of stuff planned today, but we're just gonna do a lot of practice to like reinforce the concepts from yesterday, the Diels order and electrocyclic and aromatic, anti-aromatic, non-aromatic stuff. Right. So electrocyclic reactions are going to be two types of reactions, ring opening and ring closing. And here's a chart that's useful to do these types of reactions. If you have an even pair of electrons that are participating in the reaction, or an odd pair of electrons, under different conditions like heat or light, you would get different rotations, either conrotatory or disrotatory. So what conrotatory means is that conrotatory, you are going to rotate the groups in the same direction. Right. And the direction that we rotate the groups in are either going to be clockwise or counterclockwise. Okay. So this rotatory would be the opposite of conrotatory, where the groups are going to rotate in the opposite direction. Right? So if one group rotates clockwise, the other group would have to rotate counterclockwise if they are going to rotate in this rotatory manner. So here is something called the thumb rule that I like to use for these reactions. Right. Let's separate these into two reactions, ring closing and ring opening. Where you are going to start your thumbs in a certain way and then end your thumbs in a certain way when you rotate these groups. And these will help you predict the stereochemistry of these groups that rotate after the ring closing or ring opening. When you're ring closing, you're going to start your thumbs either in the left or right direction and end in the up or down direction, which shows you if the groups are wedge or dash. If your thumbs are going up, they're wedge. If your thumbs are going down, they're dash. The more important thing here is the relative stereochemistry relationship between those two groups. Like if they're trans, then that's the most important thing, where one has to be wedge, one has to be dash. If they're cis, like your thumbs would either be going up or both down. That means that there would have to both be both dashes or both wedges, right? So that's why ring closing. For ring opening, you're going to start your thumbs in like the opposite way as ring closing. You're going to start up or down, and then you're going to end your thumbs left or right. Right. And in all of these reactions, you always rotate either clockwise or counterclockwise. Right. So let's look at some examples on this, where this table here is going to be useful to determine. Wait, not that table. This table here is going to help us determine what kind of direction the ring opening or ring closing is going to be in. Right. So we see in this structure here, this is happening under light. We see that this is not in a ring, but we can form a ring by doing these kind of arrows, right? Where a new bond is going to form between these two carbons. And it could do that by moving this double bond to make a new bond there, right? this double bond here can make a double bond there. This double bond can make a double bond there. Drawing out the template of what we know the product is going to be, it should be like this right here, where we have a new bond here that was formed from that double bond, and these two double bonds that came from these two double bonds right here, they just shifted, right? But now we still see that we have methyl groups on this carbon and this carbon, but we don't know if they are going to be wedge or dash. This is where we use the conrotatory and disrotatory thumb rule thing. Right. So here is the thumb rule. How many pairs of electrons are participating in this reaction here? Yep, 6 electrons or 3 pairs of electrons, right? 1, 2, 3 pairs, which is an odd pair. Odd pair of electrons, and we are in light photochemical conditions, which shows that we are going to rotate groups conrotatory. So that's the first step. Figure out if you are going to open or close the ring in conrotatory or disrotatory from this table right here, right? You notice how the two methyl groups are facing away from each other? Let's say this thumb right here is going to face to my left side. This thumb right here is going to face to my right side, right? We said that if we are ring closing, we're going to select our thumbs left or right and end either up or down. And we have to rotate clockwise or counterclockwise. Let's say I rotate my left thumb clockwise and it ends up, going up, right? Since this is counter-rotatory, I would have to also rotate this thumb clockwise. So this ends going down. You notice how these two cells are trans to each other, one is up, one is down? That shows that the methyl groups here would have to also be trans to each other. One has to go up and one has to go down. Like that, right? It could have been the other way as well, where that other way is just the enantiomer version of it. Now, if your reagent wasn't light, but you had heat instead, this is still an odd pair of electrons, 3 pairs, but it would be now disrotatory. So let's practice that with the disrotatory. This is, let's say, clockwise. That means this other term has to go counterclockwise, right? They both go up, so they are cis to each other. Or you could have said this goes counterclockwise, this has to go clockwise, where they're still cis to each other, right? So they're both going to be wedges or both dashes. Like that. Plus minus. Okay. Now, let's do an example of a ring opening. This was ring closing because we closed a ring. Let's see this example right here, right? Where the ring opening arrows are going to be like this, right here. Where we're going to move this double bond to make a double bond here. This single bond right here is going to break and make a double bond right there. That is going to give us this template right here, right? Where this double bond was formed from that double bond moving to that bond right there. This double bond is formed from this single bond breaking and shifting to make a double bond reaching those two carbons. Now, we still have a deuterium ion on that carbon and a CF3 group on that carbon, but we don't know if they are going to be an out group or an in group. What the heck? Hmm. What happened? Hmm. Okay. No. Mm. Oh, there you go. Okay, so the deuterium can either be an out group or an in group. The CF3 group could either be an out group or an in group. We don't know. To figure that out, we use this table right here, where we're going to rotate either conrotatory or disrotatory. So how many pairs of electrons are participating in this reaction here? Two pairs, right? Where two is an even pair. So we look at that column right there, right? And then we are under heat. So this is conrotatory. If we are ring opening, we start our thumbs up or down. In this case, both of them are dashes, so both groups are gonna face down. We're gonna start our thumbs down like that, right? And we said this was, what was it? Conrotatory. So both of these groups will have to rotate on the same side. Let's say this rotates clockwise. This group will also have to rotate clockwise, right? If this group rotated counterclockwise, then this group would also have to rotate counterclockwise. Where they're both facing in the same direction, like either in the right side or the left side, right? So if I rotated it, let's say to the left side, we could either get this product here, where they're both facing in the same direction, both facing up, or we could have this product right here, where they're both facing down. And there is a major and minor product here. Right. Does this make sense so far though? Like how the groups are oriented the way they are? Like this group here is facing the same direction as that group because when we rotated it, they're both facing in the same direction. This is going up, that's also going up. This is going down, this is also going down. And we know that because of the thumb rule there, right? Where these are our two products, but there's one major one and one minor one. Do you guys know which one's the major one from this here? So the major one would be the one that has the less steric hindrance. Yeah, the second one, that's right. Because our bulkiest group here is the CF3 group. That's bulkier than the deuterium ion. Think of it as a hydrogen atom. This second one here is facing away. This the bulky group is facing away. Whereas the first one here, the bulky group is like crowded with that diene right there. So there's more steric hindrance here, making this the minor product. Okay. So that's going to give us two different products, but this was major. So ring opening, in my opinion, is harder because you get different products. But ring closing, it's easier to see like if they're cis or trans, like wedge or dash. Right. So let's try some example problems. Try these three problems here, where I'm gonna give you a hint and show you where the bond is going to form by drawing these dashed lines for ring closing. Okay. Yeah. And for this part D here, there are going to be two reactions. Once you get the product for the first reaction, use that as the reactant for the second reaction here. And let me put the table down to make it more clear. Let me put it here. There we go. Yeah. Yes. Oh, they say the other one negative or
Yeah, because they're saying that the EEG is also going to be methyls of EW.
Oh, no.
Oh, I feel like that really is.
Yeah, that would be minor. Like this would be the major.
Okay, right. And then, okay, this one. So this was the ring closing that I did. Do you only count this as one group? So you only need like one, nothing. So this, like, so I still went like this. Like I still was like, this is going out. This is going out. It's like it's three, then it's and it's heat, and it's really heat. I like that one, which is right. But like, I was curious if you only use one from this.
One group coming out of there.
Because like this is plain.
Oh, right. it is, yeah, so if it's planar, then you can just, do what you want. Yeah,
And why is this no reaction?
this is no
I
reaction.
like this, but this is no reaction.
Yeah, it has to be like the ring, but I think it's because we're going from a unstable, we're trying to make an unstable, system, like we just had a ring string on it. It is possible to go backwards though, to go from here to here, because we're taking the ring string and becoming more, stable products here. But in this reaction, we're trying to make it an unstable thing.
Okay, yes. Oh, yeah, this one, okay, I wasn't entirely sure. You probably mentioned this yesterday, I remember you said something like this one you diastereomers because there's no pre-existing house owners.
Yeah.
But on the key, like in Mariah's video, and also on this key, she like, because then I only drew these two, but in the key, then they also drew like the diastereomer.
Oh, right. What he did was that she treated these two electron and drum groups as, the same string, where she treated that term as positive charge as one set of the answers, and the other term as another positive charge.
Yeah.
She flipped it upside down.
Yeah. I ended up with these two,
Mhm.
so I got 4 products, but then the key has 8 products, because then they also drew like these as a diastereomer. This is diastereomer, this is diastereomer. So that's how I'm assuming they did it. Because I believe that's the only way we'll be able to get this product.
Right. Where this one here is like different because,
This one's wedge, this one's dash.
Yeah.
They're the same.
and then, but they're clear. Yeah. These are constitutional isomers to each other here.
Yeah, and then, so these two would be diastereomers, and then these two are constitutional. Because then there's no, like, technically, there's no chiral centers until you make
Yeah.
the product.
Yeah, so you make it out of right. These here are diisomers because that concentration stays same, that concentration changes. Right?
I guess, I don't know, because Mariah mentioned it like that, and then I guess I'm just keeping, but what you're saying is also valid as well, because there is no chiral center when you're starting material.
In that material, right? But what they did was they the dienophile, not worrying about the strength of the electron and drum groups.
But then how would that make 8 products? I guess that's what because I got 4 from flipping it.
Important.
Because I got this is racemic, then that's racemic because it's the constitutional isomer.
Right. And you got these. I got the 4 products that you got originally, and these are the other 4 here. Yeah. So these ones here, they came from. Let's see.
So let me make sure that I really don't know.
Yeah. Let's see. Oh wait, you got this one right? Like how they put the guiding factor down.
Yeah.
And then we made. Okay, I think it would make more sense. Let's say you know how we want the EWG set to the alpha groups. These are the alpha groups, right? Like the isopropyl and the alpha group. These two sets of products here, the aldehyde was treated as the EWG. So the aldehyde is sent to the group right there. The only difference between these two are that they are the dienophile split, right? Like if the EWG is down here, the EWG is
Now
down
you're
here.
treating that's there.
Yeah, right. But then that's considered EWG here. In these sets here, the EWG is considered the nitrile, but they're just flipped.
Okay.
Right.
Okay, that makes sense then. So I was like, yeah, maybe if it was like this and then that would be diastereomer. Then you get even more.
Yeah, you give it more color.
Yeah.
So that's gonna be like more complicated.
Yeah.
Yeah.
But that makes sense.
Yeah. Yeah.
You post your lecture notes like from last house lecture. On the campus.
Oh yes, I did for today.
Okay,
Right.
so I slept through lecture.
You still do lecture? Oh, okay. Yeah. I still got like read notes for last week and then remake it, which I wrote at 11 meeting.
Yeah, because I tried looking through the notes and like getting them.
Been ready. Oh yeah.
If you kind of just go over what you did in that, so it's.
Yeah, we did. The aromatic, anti-aromatic, or non-aromatic stuff. Oh, wait, the thumb rule, so. Let me show you on the screen actually. Yeah. Right, so the thumb rule is this right here. So let's look at an example problem on that. Let's look at this one here.
Oh, when did they draw?
Okay. Yeah, I did order, great. So let's, draw the arrows of the ring closing reaction here. We know this is ring closing because we see that on like a bond. So we're gonna move that double bond to make that a single bond. So this double bond to make that a double bond there. Okay, now let's draw in that template as like that, ring that we just one. And we do have a here, right, with the direct, but we don't know if they are white or not. If we figure it out, this is where we use the thumb rule. So you know how the other groups here are facing away from the one facing up, the other one facing down. So that's why our thumbs left to right, because we are really closing here, so we start our thumbs left or right, depending on where the groups are relative. Now let's determine if this is converse or just for the chart. We know there are 3 pairs of electrons participating in resonance, so that's an odd pair. And now let's start our thumbs opposite each other. Converse term is that we can rotate the groups on the same direction, clockwise or counterclockwise. Let's rotate our left thumb clockwise or season to make that thumbs up thing. So that's clockwise. Then this may also rotate clockwise. So go down. And to each other. Oh, what is right from that? Oh, or counterclockwise. We could have done it the other way as well. Like counterclockwise is same direction.
Let's say, yeah, let's say.
I just chose clockwise. You could have chose counterclockwise as well. But what does that mean? This group has to rotate. It was the same direction.
It's in the same direction also to go
Counterclockwise.
Okay, so no, this is trans.
Uh-huh.
So it's
Oh, not always the case, because you're here, right? Let's say you're taking,
It's bringing.
or it's the like, just like then.
This is like. Yeah. that is okay.
Oh, if there's nothing, they're going to use the front row. Oh, it's because in that way. There's a single. Yeah, right.
Well, what did I review?
Oh, no, like not connecting to one.
Oh,
Just like, like that, right? Instead of going down.
There's.
Right, so now you know they're facing the same direction. So we can try to set this. If they're contrary, one will use clockwise. The other one will also have to rotate clockwise, which is what it is. So it depends on what it says.
But two substituents. Wait, these,
Yeah, I call it.
these are gonna like spin. Just rotate, this one, they're not, I mean, it's, they're spinning in like opposite direction.
Yeah, three pairs of electrons.
Is when they're spinning together. I think that's just a video.
So this is actually basically like this is like this.
Right.
So it did not be like.
This is, yeah, they're rotating different directions.
Let's see.
Similar.
So how is it without?
So like this. I
Rate
don't remember what, which one was the first, for example, I think he said like this. Oh, yeah, like that. So.
Oh, this is
closing,
even
like
thing
this.
here? We did practice. Yeah,
This.
yeah, he wrote it. This is.
Oh, it's like this kind of is just like all like
Together.
So probably one.
So.
With the start left.
Okay.
Yeah,
So this is.
Yeah, I'll
yeah,
show you.
yeah.
So you would need the. First you do the chain series.
Right, start left, right, when we're really closing.
How do you start?
Oh, wait, so, we have to look at the
Yeah, so
relative
this is where
direction
the
of the equation here. You know how this method
For
is
closing,
like up,
I don't know
right
which
there,
one.
this method is going down.
Let's say for
So
example.
they're opposite direction. So we have to figure out what it is. Are you in one right?
If they're like.
Yeah.
And if it's not.
And that would be like this.
Direction,
Up there.
but you're starting like
But they're both
left and right.
get away.
Yeah.
And then the reaction.
Thank you. Social.
Alkynes, there's deals alder.
And then
There's
spin
no
them.
electrocyclic, there's no sheets here. So
Right, so
so if
you just
anything go
drink
like
it.
that, with this.
Yeah, so do you want to yeah, and then since it's yeah.
What the? Okay. Okay, let's look at part B, where this is going to be a ring closing reaction, and the arrows will look like this. Let's draw in that template of the product, which will look like this right here, where we know that this group here is still attached to these two carbons right here that recently got a new single bond, but we don't know if these are wedges or dashes. And to figure that out, we have to do the thumb rule, rotate the groups counterrotator or disrotatory. So we know that there are 3 pairs of electrons that are participating in that reaction, which is an odd pair. And we are under heat, which is disrotatory. So let's put disrotatory there. We see that this group here is facing up towards the pocket, like away from the pocket. And we see that this group down here is facing down away from the pocket. Right. So in that case, are they going away from each other or going in the same direction? Are they opposite direction or in the same direction right now as they're drawn? Opposite direction, right? So that means that if we are ring closing, one has to be on the left side, the other thumb has to be on the right side. They have to be on the opposite side as well. Now let's do the disrotatory thing, meaning that they have to rotate on opposite direction. If I rotate my left thumb clockwise, I have to rotate my right thumb counterclockwise, right? Which makes them both going up or assist. I could have chose counterclockwise as well. Like if I rotate this left thumb counterclockwise, that means that this thumb has to rotate clockwise, making them both going down, but they're still cis to each other. So they can either be both wedge or both dash. Right. So the answer here is that we know they are cis to each other. So they could either be both wedge or they could either be both dash, which is the enantiomer of that. Right. Does that make sense? Or right. I think the confusing thing here is like like for me, the most confusing thing is like the rotating clockwise. I always have to think about like what's clockwise, what's counterclockwise. Yeah.
Isn't it?
All right. So we have 3 pairs of electrons, 1, 2, 3. Odd pair. So we look at this column over here, and heat, which is this rotor. Okay. The other way that you can think about it is like the 4n plus 2 or the 4n thing, but I like to think about as even pair or odd pair of electrons that are rotating. Right. So for this one here, this is ring closing where the arrows are going to be like this. We're going to make a nil bond between these 2 carbons up here. And this double bond here is going to move and make a double bond right there. Let's draw in that template, which is that cyclo routine right here, where we made a double bond from here, and this is the new bond that's formed from that double bond right there, right? And coming out of this ring, we have a 1, 2, 3, 4, 5, 6, 7, 8-member ring coming out of that ring, right? But that 8-member ring will expand out into the shape like this. Right? Where these 2 carbons here are going to open up to these 2 carbons right here. Right? But now we don't know if these bonds are wedge or dashes. To figure that out, we have to do the thumb rule, where how many pairs of electrons are in this reaction, are moving in this reaction? 2 pairs, which is an even pair, and we are under light, which is disrotatory. Right? Okay, so now notice how this group here is going towards the pocket. this group here is all going towards the pocket. So they're both facing like this. Right, towards each other. And if we are this rotatory, we're gonna rotate, let's say, this left thumb counterclockwise. This one would have to go clockwise, right? So a lot of people get confused because a lot of people think this rotatory is like rotating opposite direction, right? They always assume that these bonds are opposite from each other, like one is wedge, one is dash, but that's not the case. What this rotatory and counterrotatory means is like the direction you rotate them in. And then after you rotate them, they don't have to be opposite from each other. They could be from each other, right? Because if we start our thumbs facing towards each other, like these two groups are, and we rotate one counterclockwise and one clockwise, they're both facing on the same direction, which makes them cis, not opposite, right? So they both have to be either wedge or dash. Right. Wedge or dash, which is the enantiomer version of that. Right. Any questions on these parts? Yeah.
Just wondering, why would we create a bond, right there?
Oh, right. So this is like basically unfavorable. But for this reaction, there's only one spot for this double bond to go to, which is between these two carbons right here, where the sp2 carbon and sp2 carbons meet up to make a single bond there. It's like in the previous example, the sp2 carbon and the sp2 carbon here meets up to make a single bond there. We can make a bond from here to here because like when we do that, there's no double bond to move to shift, right? That's gonna break the octet rule because this carbon here already has 4 bonds. If we try to make another bond there, that's gonna have 5 bonds. But we can make another bond to this carbon here. It will still break the octet rule, which is why we have to move this bond that side, so it maintains the octet rule. If we're adding another bond to that carbon, which is this new bond, we have to move another bond somewhere else.
So whenever we see this type of reaction where it's like either lighter heat or just lighter heat or yeah, just one of those, is it safe to assume that seeing that there's like some sort of conjugated system, even partially, that it would be this sort of thing where it would just be a ring opening?
Yeah, ring opening, ring closing. Yeah.
Thumb rule, can you explain one more time how we know if we start with my thumbs up, right, or facing?
Yeah, so for the thumb rule, we are going to start our thumbs left or right if we are ring closing. Right. Where in this example here, we did ring closing because we are closing a ring, which is this ring right here. So we have to start our thumbs left or right, where that direction depends on these groups right here coming out of that, right? If we are ring opening, like in let's say, did we do a ring opening example? Like this right here, this is ring opening. We are starting our thumbs up or down, and it's easy to see because we have wedges and dashes. If you see wedges and dashes, then it's most likely going to be ring opening, where you start your thumbs up or down, right? And you can see that from the dashes, which is down, wedges up.
Okay.
Where in the ring opening, we get 2 different products because if you rotate like one way and the other way, they give you 2 different products. If you have 2 different groups, which we do have 2 different groups here, one deuterium and one CFC, where this is the major one because it has less steric groups. Let's do more practice on this. Okay. Yeah, let's do these 2 here.
Oh, this is way stronger than this.
Right. Which one way? That's one drawn group, the dad,
Than that.
the metal. So
So then when I have that one cis.
right. The outputs are always cis to the EWG.
Okay, so that would be the CN on the wedge and methyl dash.
CN on the dash, methyl.
Or, I mean, CN on the dash. methyl.
Right.
And then this one, I thought it was gonna be UP, but this made a second. And so I was like, where's the third pair one?
Okay.
It's maybe-
Oh, shoot. Let's see.
This is all just extra stuff, because literally it's just on.
I think this is all extra stuff on the card as well.
Yeah, she just.
This is lesions.
Yeah.
Oh,
Look at all the groups didn't even touch.
oh.
Oh,
This double bond here is the third one. She rotated it and moved it closer.
oh, okay, I'm not even. on-
Yeah,
I'll
yeah.
get Mascal is in there.
I don't think it's she.
Yeah. Yeah, this one I started, so like, I was able to tell the answer was.
Yeah, so this is gonna be intramolecular deal with water, or this is the diene, this is the diene file. So you have to rotate like that single bond to rotate it, or like the single bond right here.
Oh.
To make the diene file like right next to
Yeah,
that.
to make it next to the isoprene. Okay.
Yeah,
Interesting. I haven't seen them before.
yeah, this is my first time seeing like these kind of like weird.
Yeah.
Their reactions.
It's good practice, because like, honestly, even like, on her exams, her reactions weren't like big this hard, but we were able to do these. Like,
Yeah.
so you have to. Yeah, each. So, rotate this one,
Rotate that bond, yes, yes.
then it would be like, and then.
Or let's see, let's just draw, let's see. Okay, that's right.
Yeah, go ahead.
Actually, that, we can identify what there, what is it, just give me the bridge.
Yeah.
What is this?
Yeah, you know, it's not that high.
Oh, yeah, these are, these ones.
Okay, one, two, that's not the.
We went with the aldehyde, like, without the show, like, just CHO, we went it up there.
Oh, where is it?
Because this is the E, why would E be just? Yeah.
He thinks it's right here.
Right.
On the chart.
No, but you're showing them.
This also is the one.
So that you're just purely guessing.
Yeah, this means over here, also has a question from it, where you have EDG on the carbon 2 or 3, take because an increase on the poster.
Wait, I'm just, it's basically. I thought though only this one counts, because when you resonate, this one has the double bond here.
Yeah, it has, like when you do resonance here, or like, if it was like an OC3. With
Oh, that's the one.
But treat it like if you can do resonance, where if you can do resonance, we make it double bond square. Move this little bond, make a double bond there, and it's double one down there to give it a negative charge there.
Okay.
If this was also about 6 but it was also the
Yeah,
resonance,
yeah.
double bond there, and then the negative will also bond at that.
But in terms of the product, we just treat it like the map, like that, our one product, which all split.
Right, because the positive charge will be right here, because if we do resonance, we put that up there, push that up there, positive charge next. And then.
So, yeah, yeah, that checks out.
Yeah, so that checks out, yeah. So let's try drawing the arrows and then making that whole thing.
Let's go here. This go here.
Oh, this one goes at that.
So, yeah, this goes here.
And that one goes all the way.
Here. So here, one happens to this one here, this one. H N. It's like the light. Yeah, I mean, when
Yeah.
yeah, there's like a deep split.
Wait, that's what we done, that goes up,
Like,
you follow the pattern.
I didn't know that.
One goes to the left side, one goes to the right side of this.
Oh, yeah, it's like, yeah.
Opposite.
Yeah.
Clockwise, and how we go.
I mean, he hasn't
Yeah.
talked about intramuscular. Only briefly went over it. That's not. Yeah, we also said expect stuff.
Okay. So for part F, is this going to be a ring opening or ring closing reaction? Ring opening where the arrows are going to look like that and that, right? This single bond right there counts as a pair of electrons. So we count as a pair of electrons, which we see two pairs. Another way you can think about it is that the pair of electrons will always equal to the number of arrows in the reaction. So that's an even pair, and we have light, even pair light is disrelatory. So we know this is disrelatory, meaning that we're gonna start our thumbs up or down, and we can see that with the wedge or dash here. Let's say this is up, this is down. Disrelatory, I'm gonna rotate this counterclockwise. That means that this has to go clockwise like that. Or they're both facing to the left side or the same side. Let's draw in that here. Like that. Right. If I did it the other way, in this case, it doesn't matter because these two groups are the same methyl groups. But let's say this was a tert-butyl group. Tert-butyl group. Let's say I start this up and this down, and I rotate this clockwise. This would have to go counterclockwise, which is this way, right? Where they're both facing to the right now. So the other product would be like this. Now there would be a major and minor product here. Which one would be major and which one would be minor? Yeah, major, less steric hindrance, minor, less steric hindrance. But in the original problem, they're both the same because it just flipped and rotated because they're both the same groups. Right. But if there was a different group, then these would be your two different products. Okay. For this one, same kind of reaction, that template right there. But there's no group on that carbon right there. And there are two groups here. So when we create that double bond right there, this carbon was sp3 with stereochemistry. It becomes an sp2 flat hybridized carbon, right? Where since there's no other group to compare and rotate with these two groups, the tert-butyl can either go up or down, or the methyl group can either go up or down. So we get two different products. Where one product is, let's say, tert-butyl goes up here, methyl goes down here. The other product is if the tert-butyl goes down here and methyl goes up there. Right? There's a 50, so not 50-50 chance, but there's a chance to get all these two products here. Where this is the major one, because this avoids less steric hindrance. This is the minor one, because this has more steric hindrance. Right. Not 50-50. It would favor this product here with less steric hindrance. Okay, so the next thing we are going to go over is how to determine if a molecule is aromatic, anti-aromatic, or non-aromatic. To be considered either aromatic or anti-aromatic, you have to fulfill these three conditions here, all three. The molecule has to be cyclic in a ring, the molecule has to be planar, flat, and the molecule has to be fully conjugated. It could do resonance all around the ring, where the ring has to have all sp2 atoms. If there's an sp3 atom somewhere in the ring, it is not fully conjugated. If the molecule is missing one or more of these conditions, it is automatically non-aromatic. Right. So in aromatic and anti-aromatic, if you have all of these three conditions, to differentiate the two, aromatic will have an odd pair of electrons. in the ring. Anti-aromatic will have an even pair of electrons in the ring. Non-aromatic, it doesn't matter. It could be odd or even, because as long as you are missing one of these conditions, automatically non-aromatic. It doesn't matter how many electrons you have. Right. So let's look at the simplest example here. This benzene ring here. We see that this benzene ring is cyclic, all in the ring. It is planar because all of the atoms are sp2 hybridized. And it is fully conjugated because all of these double bonds can do resonance all around the ring, right? So all three conditions are fulfilled, where we see 1, 2, 3, 3 pairs of electrons. 3 pairs of electrons in the benzene ring, which is an odd pair. So this benzene ring is aromatic. Right. And the lone pair of electrons, the pair of electrons does not have to be a double bond. It could be a lone pair of electrons. So let me give you guys an example of that here. Okay. So we see that this molecule here is cyclic in the ring. It is planar. And is this ring fully conjugated?
Yeah, yeah.
Yes, because what does this nitrogen have that's not drawn out right now?
I mean,
A lone pair of electrons, right? Where that one lone pair of electrons can do resonance with the ring, like that, right? So this is fully conjugated. Or how many pairs of electrons are doing the resonance in the ring? 6 electrons or 3 pairs? 3 pairs, 1, 2, 3 pair, or an odd pair, making this aromatic as well. Okay. So let me give you guys some practice problems on this, and then 3 oddball examples, 3 weird examples of this here. Okay. Let's say we have that. And on the exam, he will most likely not give you the lone pairs of electrons. He'll just put like neutral or negative charge, where you have to assume that there's lone pairs there. And to do that, you have to like be familiar with formal charges on atoms.
We're just determining aromaticity of these, right?
Yeah, determine if these molecules are aromatic, anti-aromatic, or non-aromatic. Yeah.
So when you bring ring, closing, make a polar ring, it doesn't occur in heat, but it occurs in light because you're like promoting the electrons in the orbital.
Oh, the orbital theory stuff, I'm not too familiar with, but is that like the case, like why there was no reaction under heat, but there is a reaction under light?
Yeah, I just did an example with light, and then
The reaction did
so I'm
happen?
assuming it has to do with because you're like exciting the electrons when you're doing.
Oh, I see. And it's able to go to the anti-orbital or non-orbital.
Yeah, because you're
Going from homo to lumen.
Homo to Luma. Oh, I see.
electrons going from homo, because you're making a move. Right?
No, you're changing the number of parts.
Oh, dang. Yeah. And the heat doesn't do that, right? The heat doesn't excite the electrons to the.
Well, we're
the
confused
Luma.
about that, because one of the problems is,
Yeah, because like the one from Levens had heat and it was no reaction, but then the one on Rise and it's light.
Yeah, it also depends on the professor. Like,
Yeah.
what I would ask Pascal like what he thinks about that as well, just to be 100% sure for him.
There's the presence of the paired
That's what we're
like what's like
Oh, yes, it does. Where if the lone pair is able to do resonance with the surroundings,
These are
that's
nice.
that atom has
This
to
is
be.
this.
But if the lone pair on the atom is not able to do resonance, then that atom is serious. That's the
Okay, so it's
Yes. Yeah, fully conjugated meaning that all atoms in the ring are participating in resonance. Like, and there's resonance all throughout the ring. Right. That, or another way to think about it, it's like all atoms in the ring are sp2 hybridized. If there is an sp3 atom in the ring, then it's not fully conjugated because that sp3 atom cannot be resonance. It blocks the resonance. Yeah.
Yeah, this chapter 15 aromaticity stuff is easier than chapter 14. I think like easier than the Diels order reaction and the electrocyclic conjugated dienes. Like, with the benzene reactions, it's easier than chapter 14.
it just feels though like he's just pounding so much content.
Like the rate of it, yeah, it's just a lot.
you didn't go over hetero atoms.
Oh, he didn't go over hetero atoms and rings like this?
No. I don't know why he did it.
Oh, yeah, but it's a common example, like common thing tested, yeah. I think he, like, I noticed like Pascal, he goes over simple examples and then he tests on like the examples on the textbook. So like, even though he didn't go over it, he could test it, so because he didn't go over ring expansion too for the last midterm, but ring expansion was on the midterm.
I think he assumed that we knew range expansion beforehand.
Yeah, he just assumes that, this, I think, I don't know. It's weird. Yeah. But I think we did go over ring expansion during the concept review session, sometime.
Yeah, we did.
Yeah. Yeah, if this was an oxygen
No,
with no H, that would work as well.
Okay, so for this first one here, what did you guys say? Oh shoot, say was the thing aromatic, anti-aromatic, or non-aromatic? Yeah. Anti, right, because it does fulfill all the conditions. It is cyclic, planar, and all conjugated because all of these atoms in the ring are sp2 hybridized, and we have 1, 2, 3, 4, 5, 6 pairs of electrons, which is an even pair of electrons, meaning anti. Don't get confused because a lot of people think even is a nice number, it looks like a nice number, and they think it's aromatic, but it's the opposite. Odd is aromatic, even is anti. Yeah.
Wait, what did you say about like the double bond existing as a radical when it's anti-aromatic? So I was really confused when you said the double bond is more likely to exist with two radicals.
Oh, that's for the cyclobutene case.
Is that only for cyclobutene?
Cyclobutene, I think so. I'm not too sure about that because that was my first time hearing about the diradical thing too. Like when it was so unstable that it's more likely to exist as a biradical like this, where we have cyclobutene like that, where it's most likely to exist into this form here. Something about ring strain or something like that. I'm not too sure. Yeah. Right. Let's see. Okay. What about the second one? Right. So let's see if the three conditions are fulfilled. It is cyclic, right? It is. Yeah. The top carbon here is sp3 roadblock. It blocks resonance. It is not fully conjugated. So that condition C is not fulfilled. That makes it non-aromatic. Right? Okay. Third one? Non. Right. So what conditions is not fulfilled in this example? Right. Aromatic, right? Because we see a negative charge here. That means that that carbon has one lone pair of electrons, where that one lone pair of electrons can do resonance with the ring. And that means that we have 1, 2, 3 pairs, which is an odd pair. That makes it aromatic. Nice. Aromatic. Okay. This one? Non, right? Because we have sp3 atoms in that ring. Non. Okay. This one? Right. So anti, it is fully conjugated, cyclic, and planar, but how many pairs of electrons are doing resonance? One pair, right? So it is aromatic. This positive charge here means that this carbon is missing electrons, but it's still sp2 hybridized because it has an empty p orbital. If that was a negative charge instead, then that would be anti, because that lone pair would count as a pair, but there's no electrons there. It's just this one pair. Next one. Yeah, aromatic, fully conjugated, cyclic, planar, 3 pairs, 1, 2, 3. There's no lone pair of electrons on that positive charge, so aromatic. Okay. Next one. Yep, anti. Nice, nice. Yeah. Okay, this one might be a little tricky one, maybe, with the nitrogen in the ring as well. Yeah, it is aromatic because this neutral nitrogen here with 3 bonds has one lone pair of electrons, right? If this lone pair of electrons is not able to do resonance, it is sp3. But we see that it is able to do resonance, so that makes that sp2. Where this lone pair of electrons counts as a pair in the system, so that's 1, 2, 3, 4, 5 pairs of electrons. That's an odd number, making it aromatic. Okay, let me get, yeah. Yeah, the lone pair here. Yeah, so that's gonna go over the oddball example here, where even though there's a lone pair there, there's one example where it cannot do resonance. Yeah, so let's go over those oddball ones here. So let's say we have something like this. Right. The nitrogen in this ring has a lone pair of electrons, but if we see it also double bonded to another atom in the ring, right? that nitrogen's empty not empty p orbital, p orbital is already occupied with that other atom. So that means that this lone pair of electrons here is not in a p orbital. That is in an sp2 orbital. So that lone pair of electrons is not resonating. It's stuck there because the double bond is taking the resonance power of that nitrogen. So if there's already a double bond there, that lone pair would not resonate. In the previous example here, this lone pair was on this nitrogen that was not double bonded to the other atom.
So nitrogen is not double bonded. It cannot.
Yeah.
Okay.
If a nitrogen is double bonded, a lone pair can't do resonance. The thing that is doing resonance is the double bond itself, right? Like the double bond here is doing resonance with the ring, right? Where it is not anti-aromatic because some people might think this is 1, 2, 3, 4 pairs. They count the lone pair as well, but that doesn't count. The only things that do count are these pairs of electrons in the ring itself, making that aromatic because that's an odd pair. Right. Okay. Another odd example is a carbonyl in a ring. So let's say we have this ring right here with a carbon double bond oxygen. You can't figure out how many lone pairs of electrons are participating here from what it's drawn as right here. You first have to draw this resonance structure where we push the double bond onto the oxygen, draw its resonance structure to give that oxygen a negative charge and this carbon a positive charge. Then we do the aromaticity determination thing here, where we see that there are only 2 pairs of electrons doing resonance in that ring, which is an even pair, and that is anti-aromatic. Right. Right. This double bond here does not count as a pair of electrons. So you can't say this is 1, 2, 3 bonds, odd pair aromatic, because that is not participating in the system. We have to draw its resonance from the carbonyl, giving that carbon a positive charge where there's no electrons there. So if that doesn't count, then we only have 2 pairs from these double bonds here, making it anti-aromatic. Right? So the other weird example are non-planar molecules like this. And right, when you see this structure here, we know that there are hydrogens on these carbons, but they have allosteric hindrance because they're so close to each other. So the hydrogens would prefer to pucker the system where one hydrogen is going to avoid the other hydrogen by one being dash, one being a wedge, right? Where they're going to go in opposite directions, making them non-planar. This is supposed to be non-aromatic, but in lecture today, he said that it will just be aromatic. So he says that this structure.
That was non-aromatic.
Yeah, it is non-aromatic. It's supposed to be non-aromatic, but in lecture he says this is aromatic. I got confused when he said that
Isn't it
too.
locked in the transconfiguration, so it can't rotate, like.
Yeah, it's not planar. It's pucker because one hydrogen is pushing one benzene down, one part of the ring down. This other hydrogen is pushing the other ring up. So it's like that. It's not planar. So it's supposed to be non-aromatic, but Pascal says this is aromatic. So I got confused when he said that.
2 things.
Uh-huh.
One, are those hydrogens like naturally implied just because of the orientation of the, like the already like bond rings like up there?
Right, the geometry of the bonds here are so close to each other that they force the hydrogens away from each other to avoid steric hindrance. But in lecture, Pascal said that aromaticity is a favoring factor that will make it planar. But I've never heard that before. I've always heard that this is non-planar, but Pascal says it.
Yeah, I saw that. I was really confused.
Yeah.
I like wrote in my notes like.
So like, should we write on the test non-planar or just like we gaslighted it to like just calling this aromatic?
I would
Ask Pascal
Okay.
as office hours. Yeah. But that's scary though. That like asking Pascal. I think.
Yeah, he said it like it would contort itself to try to be planar to avoid.
To become aromatic,
Yeah,
right?
yeah.
Because this is 1, 2, 3, 4, 5 trides electrons, which is an odd pair. And if this was planar, it would be aromatic. And that's what he said. Like aromatic is like a driving force for this to be planar, but I think steric agents here makes it non-planar and non-aromatic. So I don't know. What would I put in the test? I would put non-aromatic in like 5 points back, like because you're good for that. Yeah. Because even the TAs, I think the TAs know that this is non-aromatic too.
Yeah.
Well, it's Pascal's task, so like he chooses the grade at the end.
With the other ones also not right? I think that.
Yeah,
This 8-membered ring right here is a boat shape in 3D. It bends into a boat shape like this. Right, so this is non-planar. Where Pascal says this is non-planar as well. So this is safe to say non-aromatic. This is also supposed to be non-aromatic, but I'm gonna make a note here for Pascal's class. So those are the 3 oddball examples where
the lone pair is on an atom that is already double bonded, where that lone pair cannot do resonance. The other one is the carbonyl, carbon double bond oxygen double bond does not count in the system. The other ones are the non-planar rings like this. Yeah. Yeah.
The first example, you draw one more time without the orbital.
Yeah. Let me try one more time without the orbitals. Let's see.
Where that lone pair is not counted as a pair in the conjugated system because this atom here is already double bonded. Where that double bond there is the one that's in resonance with the ring. Carbonyls, it could be iminium as well, like where instead of an oxygen, it could be nitrogen. So a carbon double bonded to another heteroatom, like not a carbon, right? Like oxygen, nitrogen. Yeah, those are the common ones. Oxygen, nitrogen. Yeah.
Okay, let's try these examples here. So for the series class, she just gives examples where you have to assume that it's planar. You don't have to worry about like non-planar things. So I'm just gonna say the ones that are non-planar, so you don't have to worry about that. This is non-planar, this is non-planar, and this is also non-planar. Everything else is planar, so don't worry about the planar condition. Yeah.
But the second one, the bottom, I know if you follow the rules, it's anti-aromatic,
Yeah.
but like. I thought you can just treat it as 2 benzenes because it's separated. So it would be stable.
Oh, right. So these 2 benzenes here they look separated, but they're actually conjugating each other because
Yeah.
this can move here and resonate with the other ring.
But it really doesn't want to be anti-aromatic though. So why
Uh-huh.
couldn't you just treat it as 2 benzenes because it's not going to do that? Like it doesn't want to be conjugated.
Yeah, it doesn't want to be conjugated, but it's forced to be conjugated because it's like connected by this bonds here, right? Which forces it to be anti-aromatic there, right? If those bonds weren't there, then there would just be 2 separate bending rings. But since they're connected, then they are conjugated because they can do resonance through this like channel here.
But why can't it just not do resonance and be 2 benzene? It can like. It doesn't have to. It can be like a really minor structure.
Yeah, well, I'm not sure but it's just like a question thing, like, they're just asking if it's like aromatic, anti-aromatic. Maybe in nature, like, this doesn't exist because it's anti-aromatic, but this is very unstable because it's anti-aromatic, so maybe this doesn't exist in nature, but it's just like a conceptual question, like, asking you to determine if the structure is aromatic, non-aromatic, anti-aromatic. But you're right, like in nature, like, this probably doesn't exist. Or it just exists for a brief moment, and then it goes back to the aromatic thing through the orbital, like, or like bending the shape or something like that to become non-aromatic, right? Because I think, well, I think in lecture he said like this here will bend itself to become non-planar to become
That can't
non-aromatic. Oh,
There's no way.
the way to bend, yeah. Right, I think it's just like, yeah, very unstable, it doesn't exist, yeah. Yeah, but you're right, this is anti-aromatic because everything is cyclic, fully conjugated. What was the other condition?
SP2 hybridized.
Yeah, fully conjugated, sp2 hybridized, cyclic,
Wow.
flat, right? Everything is planar,
Planar.
planar, right. And also we have 1, 2, 3, 4, 5, 6 pairs of electrons. That's an even pair, anti-aromatic. Yeah. So it's more a conceptual question. Well, where this like probably doesn't exist very long in nature because it's so unstable.
Anti-aromatic.
Oh, right, so after you get rid of there, this creates a single bond, these two pairs, so is that minus eliminate? So there's one of them, and that's the one, it's one, this is the one.
You can't draw them again.
And then once you get it, keep it like again, it will open up. So that sounds like we'll open the one that, and this is the one that's done. This is going to be very open.
Like that, and that's a new side of the function. Functioning.
Very, 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 yeah.
It's all complicated, but it's.
Like physically, you would be able to only count that, so like it's like. Right.
Yeah, it's between two SMG.
I always want to draw because it's small.
Yeah.
Wait, why do you?
But this is like.
Oh, there's one there.
No. So I was like. We just like.
This one here is going,
What draw? How about this one? So they're in the same direction, right? And then I mean, that's more like same direction, that's right. Both left or both right.
Okay,
Very right.
and if they were going different.
Yeah, that's.
yeah, like if this was slowing down, this is slowing down, this, or this, giving you the muscle going down. Then the
This is interesting. I want to find another practical sheet for.
what almost doing, yeah, this either this way, but
Okay,
yeah.
that makes sense.
Yeah, no problem. Oh, this one here. Well, yeah, so that carbon there is an EDP, so it was quite the negative, right? Where, you know how this is the diene right here? If the diene has two on the end of it and there's an EDP there, it pushes the all the way down to the negative charge there. That's on the price. Okay, and here's a negative charge on that person there. Positive charge over there. If the, the group is here, it pushes the lower pressure down there as well. You're gonna cover more negatives. Right. So the negative charge should be on the carbon there, positive charge on that carbon. And this is an even region where.
Yes, so I was talking about this.
Giving this very possibility.
If I use the correlations, what good, and the number of like, it was really. It's like mental torture. You know, it's like we're laughing at ourselves, we're doing that. I need to find out how to make any part of it. Like I'll volunteer with my session to my friends. Yes, like,
Yes, I can.
Okay, what did you guys say for the first molecule? Aromatic, anti-aromatic, or non-aromatic?
The first,
Yes,
uh, the-
aromatic, that's right. Because let's draw on the lone pairs here. It is aromatic because it is cyclic, fully conjugated, and planar. Where the only pairs of electrons that count are these pairs right here, 1, 2, 3. This pair does not count because that pair is already on an atom that is double bonded, not being able to do resonance. It's not 1, 2, 3, 4 pairs. It's 1, 2, 3 pairs. Yeah. Next one. Yep, aromatic. Nice. Next one.
and
Yep, anti. Next one.
no,
Non, right, because of this roadblock, sp3 roadblock. Next one. Anti, right. Where in lecture, he says this is the one that exists as a biradical. So that might be a conceptual vocab question as well. Next one.
aromatic,
Aromatic, right. One pair. Okay, last one.
and
Aromatic, right. This oxygen here still has a lone pair of electrons, but that lone pair does not resonate because it's on an atom that is already double bonding. So it's not 1, 2, 3, 4 pairs. It's only these 3 pairs, 1, 2, 3, which is called aromatic. Nice. Okay. So the next thing we're going to go over is activators versus deactivators. Right. So before we go over that, let's go over ortho, meta, and para position. If we have a benzene ring with one substituent, which I'm going to label that substituent as a random R group, the ortho position is 1 carbon away from that substituent. Meta position is 2 carbons away from that substituent. Para is going to be parallel to that substituent, or 3 carbons away. Right. So these carbons here, the way I drew the benzene ring, are not always the ortho, meta, and para positions because I see sometimes people say that's the ortho, like people say this is the ortho position still, this is the meta position still, but this is the para position still. But that's not the case because ortho, meta, para are relative positions, relative to the substituent here, right?
Yeah.
Where the ortho are this carbons here, 1 away from the substituent. Meta is 2 carbons away. Para is parallel. It's not always these are ortho, not always these are meta, not always this is para. It's always relative to that substituent right there. Right. So in this case, the way I drew it, these are the ortho, these are the meta, and that is the para. Yeah. Okay. So in these benzene reactions that we're about to learn, the general pattern it follows is the electrophilic, aromatic substitution. And this is abbreviated as EAS. EAS reactions. Okay. So let's say we have a regular benzene ring. Start with a simple example where most of these reactions that you're about to learn in chapter 16 follows this exact same mechanism, but with different reagents, different nucleophiles, different electrophiles, right? And let's say we have an electrophile nearby. The carbons here of the benzene ring are nucleophilic because they have a lot of electrons and bonds in them, right? Where, let's say one of the carbons of the benzene attacks that electrophile.
when that happens, we get that electrophile attached to that carbon that attacked that. That means that this carbon right here on the other side lost the bond, giving that carbon a positive charge, carbocation. Right. This is very like unstable because we started with a stable aromatic ring. But once we did this addition reaction, we broke the aromaticity. So in this case, the aromaticity is broken, which became more unstable. Right. There is a way to reform the aromaticity. What is one of the main reactions that we can do to form double bonds?
E2.
E2 reaction, elimination reaction, right? Where the hydrogen that we're going to take is that hydrogen right there on that carbon. Some kind of random base, and it depends on the reaction of chapter 16. It could be a metal catalyst, it could be Cl minus, it could be SO3H, depending on what reaction it is. This is just the general mechanism of what you're going to see over and over and over again in chapter 16. Any random base is going to grab the hydrogen and form a double bond right there. That reforms our aromatic benzene ring. Right. So aromaticity is reformed. Right. So don't get overwhelmed by the bunch of reactions in chapter 16. It follows this general mechanism here. Okay. This one.
It kind of like looks like an addition, but it's.
Right. The first step is an addition. And then the last step is an elimination. Where the first step added the electrophile, and your electrophile differs depending on what reaction we want to do. There's bromination, chlorination, sulfonation, nitration, all those reactions. Those mechanisms follow the same step here, addition, elimination. Right. Where once we did the elimination, this happy benzene ring becomes a unhappy, unstable benzene ring, where the last step reforms that happy, stable benzene ring. Okay. So now let's go over activators and deactivators. We can make the benzene ring more nucleophilic. If we want to make it more nucleophilic, what kind of groups do we want to add on it? EDGs or EWGs? EDGs, right? Because we want to donate electrons or give it more electrons to make it more negative. Deactivators are EWGs. They deactivate the ring because they make the ring more positive, weakening the nucleophile power, right? So let me just say that EDGs are ortho para directors. And I'll explain this. EWGs are meta directors. And the exception for EWG are halogens, exception. And I'll go over that as well. So director means that the electric file will add in a certain carbon relative to the EDG or EWG. So let's say I have this benzene ring here with this EDG right here, OCH3. Right. I'm going to, yeah.
Won't he make us rank the ELU and EDGs if we're going into electrophilic aromatic substitution?
Right, right.
Like he has to.
Yeah,
right?
he has to, yeah.
So we're gonna have to rank it for deals older as well.
Well, Diel's order is usually given as like one EWG or one EDG only. I haven't seen an example where like there's like multiple EWGs,
But he
EDGs.
can make us-
Yeah, he could make them compare it. Where if there are multiple like EDGs or EWGs, you choose the stronger one to direct where the charges are going to be, right? And it also depends on the professor because I know Helix he prefers like the EDG strength and EWG strength, but Nasiri like she doesn't care. Like she gives you like for Diel's order multiple products based on the charges.
Okay.
It doesn't matter
For
about the
benzene, you have to do it.
yeah, for benzenes, you have to do it because this is when the ranking of these EDGs and EWGs come into play. Right? Where these are the strengths of the EDGs and EWGs, right? But there is a pattern to this. I'll show you guys these patterns, right? So let's just focus on this first. So this is an EDG right here, where it could directly donate electrons to that benzene ring, giving us this resonance structure here. Right, where we introduce a negative charge on that carbon right there. We can keep going and push that negative charge to make a double bond there, create a negative charge on that carbon to get this resonance structure here. So I'm just gonna draw out the resonance structures and let me know if these make sense. And then I have that new lone pair, which creates that double bond right there. This double bond goes onto that carbon to create a lone pair there. Yeah, 118A, 118A PTSD. Yeah. Where we see that the resonance structures does conserve the charge because we started with a neutral molecule. All of these resonance structures are neutral because the charges cancel out, right? Where EDGs, as we expected it, donated electrons and negative charge to the benzene ring. And where do you guys notice the negative charges are at what positions relative to the EDG? Ortho, meta, para?
Ortho.
Yep, ortho and para. Because that is ortho, this is para, this is ortho. So let me just draw in a general benzene ring with any EDG. We know that that EDG will create partial negative charges, ortho and para to it, right? Which means that the ortho and para carbons of this benzene ring are the strongest nucleophiles. They are stronger nucleophiles than the meta position because negative charges are better nucleophiles than neutral charges. That's why EDGs are ortho para directing. Where if we introduce any kind of electrophile, either the ortho or para position will attack that electrophile, not the meta position. Because negative charge, stronger nucleophile than neutral charge. That's why EDGs are ortho para directors. They direct the electrophile either in the ortho or para position relative to it. Right. Okay. So EWGs, I said they were meta directors. Let's look at an example of why. So an example of an EWG is NO2, which looks something like this. Right? Even though there's a negative charge on the NO2, that atom is not directly attached to the system. When we determine EDG and EWG, we look at the very first atom directly attached to the benzene ring, which is this nitrogen here. If that atom is positively charged or partially positive charged, it wants to withdraw electrons, making this an EWG, right? Where we can see it could do resonance by withdrawing its electrons from that arrow and that arrow right there. So let me just draw in all the resonance structures. Positive charge on that carbon. Do that. Resonance, resonance. And last one. Okay.
Then wouldn't the NO2 with 5 bonds be neutral?
The NO2, 4 bonds, positive charge, right? Because nitrogen is on the 5th column of the periodic table.
Yeah.
It wants 5 electrons to itself. It has 1, 2, 3, 4 electrons to itself. 5 minus 4, positive 1.
Doesn't, for the second one, I think you drew all the card. Doesn't the other option also have a negative charge?
Oh, that should be let's see, negative charge. Oh yeah, negative charge. Yeah, you're right. There you go. Yeah. Where we started with a neutral
molecule, the charges cancel out, and all of these resonance structures, the charges still cancel out to neutral because they have two negative charges, two positive charges on the other resonance structures. They cancel out to neutral. Where EWGs, they put positive charges on the ring because they withdraw electrons. And in what positions do you guys notice the positive charges are at relative to the EWG? Yep, ortho and para, that's right. So we have partial positive ortho and para. Which position is the best nucleophile in the EWG here? The meta position, right? Because neutral atoms are better nucleophiles than positive atoms, right? So there's no negative charge on the meta position, but it's still a better nucleophile than the positive atoms. So that's why if we introduce some kind of electrophile, the meta position is the one that attacks the electrophile, which is why EWGs are meta directors. They direct the electrophile on the meta position. So here's the exception, halogens. X, where X could be chlorine, bromine, iodine. Okay, because if we have, let's say, bromine here, that bromine has 3 lone pairs of electrons, but it is really electronegative, right? That right there makes it a EWG. But because it has a lone pair of electrons, we can have negative charges in the ortho and para position, right? Which is why, even though halogens are EWGs because of the electronegativity, there are partial negative charges on the ortho and para position. But halogens are relatively weak EWGs. They're one of the weakest EWGs. Weak EWG. Even though they are EWG, they are not meta directors because they have pairs of electrons that can donate into the ring, giving that ring negative charges on the ortho and para positions. So that's the exception, right? But every other EDG is an ortho para director. Every other EWG is a meta director. The only weird case is this halogen here. This halogen is an EWG, but not a meta director. It's a ortho para director because it can do resonance. It's an EWG because it is really electronegative, withdrawing electrons through induction. Right. So it withdraws electrons through induction, but it's an EDG because of resonance, giving those ortho and para positions relative to it a negative charge. Yeah.
So it's an EDG, but it acts as an EWG when you react it with the benzene.
Right, it's an EWG, but it acts as an EDG.
Okay.
Right, it's an EWG because it withdraws electrons through induction, but it acts as an EDG because it directs the electrophile in ortho or para. It's an ortho para director.
So when you resonate, it's an EWG.
Oh, when you resonate, it's an EDG because it's donating its electrons into the ring. Okay, but the induction effect in this case overpowers the resonance, which still makes it an EWG. So this is more of a conceptual question, like are halogens EDGs or EWGs? And a lot of people like always remember that halogens are ortho para director, and they connect ortho para directors with EDGs. So they say halogens are EDGs, but they are not EDGs. They are EWGs because of their high electronegativity. Right. But even though they are EWGs, they are not meta directors. They are ortho para directors. So this is the only exception here, where it's like the opposite.
And that causes like electrons to be drawn up into it.
Yeah, the induction effect causes the electrons to be drawn up to it, but because of the lone pairs, they donate electrons, giving that benzene negative charge in the ortho and para position. Okay.
Yeah.
Where these are the nucleophiles that would attack the electrophile. So there are different strengths of EDGs and EWGs. Okay, let me give you guys general patterns of these first. So I'm gonna give you characteristics of a strong EDG. So a strong EDG will have
negative charge, which is more electron donating than something neutral because they have full negative charges. What the? Another characteristic is that the atom is less electronegative. Less electronegative atoms are stronger EDGs. Stronger, more electronegative. So an example is, let's say, NH2 and OH. NH2 here is a stronger EDG than OH because we know nitrogen is less electronegative than alcohol, than oxygen. Since nitrogen is less electronegative than oxygen, nitrogen is more willing to give its electrons and donate its electrons. Oxygen is more electronegative, which means that it wants to keep its electrons. It doesn't want to donate it as much as nitrogen does.
So it's like nucleophile rules.
Yeah, like nucleophile rules. Right. EDG are like nucleophile rules. Negative charge stronger than neutral, less electronegative, more or stronger than more electronegative. Right. Yeah.
So are all strong EEGs also strong nucleophiles?
All strong EDGs are also strong nucleophiles. Yeah, you can think of it like that. Yeah. The weird one is our R groups, right? Because R groups, they are EDGs through induction. They have no lone pairs of electrons, so they can't do resonance. They just donate electrons inductively, which makes them weak EDG, because they don't have lone pairs to donate directly. Strong EWG is like a strong electrophile. Positive charge, better than neutral. Another thing, let's see. Let's see. More electronegative atoms, negative atoms nearby, better than less electronegative atoms. Atoms nearby. Because if you have electronegative atoms nearby, that atom becomes more positive, which makes it a better withdrawing group because it wants to gain more electrons. So it's like the electronegativity rule, electrophile rule. An electrophile becomes better if there are electronegative atoms nearby. So an example would be something like this. Let's say we have that carbon bonded to 3 fluorines compared to this carbon bonded to 1 fluorine. This carbon here that is bonded to 3 fluorines has a bigger partial positive charge than that carbon with only 1 fluorine. Since this carbon has a bigger partial positive charge, it's a stronger EWG because it wants to withdraw electrons more than that other carbon. So here's the list of the strengths of the EDGs and EWGs, where, oh, another thing before I go over that list is, let's say we have activating power, right? Strong EDG is the most activating, which is over weak EDG, right? But which is a better activator, a strong EWG or a weak EWG? Right, so we want a weak EWG because what does EWG do? Does it activate or deactivate the ring? If we had an EWG on the ring, it deactivates the ring, right? So we don't want to deactivate the ring as much. So that means we want a weak EWG. A weak EWG is a stronger activator than a strong EWG. So a weak EWG is a stronger activator than a strong EWG because it doesn't deactivate the ring as much. Strong. Whereas the strong EDG, we want that to donate a lot of electrons to the ring, which makes that the strongest activator. The strong EWG is the strongest deactivator because it withdraws electrons the most. Weak EWG is stronger activator than strong EWG because it doesn't deactivate the ring as much. And then weak EDG is like right there in between them. So here's the activating power. In this list, the very top ones are the strongest EDGs. The very bottom ones are the strongest EWGs. The one that is in the middle is a hydrogen. That's not an EDG or EWG at all. The weakest EWG is a halogen, like bromine, chlorine, iodine. Yeah, and then the weakest EDGs are any R groups, like methyl, ethyl, propyl, isopropyl.
It's like a redox star with the groups.
Oh yeah, like PCC, Jones, something like that.
No, like.
Yeah, just like oxidizing potential and reducing potential, like how like the weakest oxidizer can get.
Oh, yeah,
inverse
it's like that
reducer, yeah, it's
spectrum.
like inverse.
Invert,
Yeah.
yeah. But in Gen Chem, right? Where the EDGs are orthoparadictors, EWGs are metadirectors, except halogens. Halogens here, they are orthoparadictors, but they are EWGs.
I know Mescal has or since it's your first time with like Mescal, you're probably
Yeah.
not gonna know this, but with your experience with other teachers, how much of this are we kind of like expected to know?
So Helix, I know for sure, he provides a whole list of the rank of the groups and what you need to know. Like, this is not all you need to know. You need to memorize all of these. Helix gives you like a feel only. Nasiri, she doesn't give you a list. She just expects you to know. For Levens, I've only seen Levens teach A and C, and I haven't seen Levens teach B, like as a tutor. Mescal, we'll see when he goes over this stuff here.
So what is the energy of the charge?
Oh, right. So the NO2, it should be like neutral. Yeah, you're right. It should be neutral. Because the NO2, it looks like this. I just wanted to show that that N right there has a positive charge and the oxygen has a negative charge right there. Right. Where there's a positive charge on that nitrogen and one of the oxygens here has a negative charge like that. Right. Where we see that this nitrogen has a direct full positive charge, making it a very strong EWG. Right, that's a good catch though, because this nitrogen here has a positive charge, no other atom has a negative charge. But because these charges cancel out, that NO2 overall should be neutral. But I just wanted to show that that nitrogen itself has the full positive charge, which is the direct atom attached to the system. But overall, it's neutral. The NO2 is neutral because of that negative charge right there. But ignore that oxygen with the negative charge because that's not the atom directly attached to the benzene ring. The atom that is directly attached is this nitrogen here with a positive charge. Okay, now let's do the Kahoot. Yeah. Yeah, no problem. See ya.
Out of curiosity, have you ever TA'd for any?
No, but I am in the grad level OChem class right now this quarter and last quarter, so I know some of your TAs in like Mescal's class and the TAs in 118 CE. Yeah. Wait, what?
They grade well.
Do they grade well? Some of them are strict. Like they actually care about. Some of them they don't want to be there. Like they don't even want to TA. They just want to be there for research and stuff like that. So they like give random points.
Anyway,
Some people are so passionate.
Yeah, like those TAs are chill. Like they yeah.
If you were to,
Uh-huh.
how would you grade?
I would grade pretty leniently. I would say yeah.
But you like focus a lot of the time in discussion, like actually doing these concepts.
Oh, like the content review and stuff like that. If I was a TA, I would be a grad student, but I won't have time to do all these stuff right here, like to prepare things. Because right now I'm just a part-time student that like I have a lot of time. Like I'm just taking like 7 units. So I have a lot of time to do like this, like preparation and stuff like that. Yeah, yeah.
Stuff for this, like you have your office hours, you do all the tutoring.
Oh yeah.
Go
Yeah. Okay. Let's go. Yeah, I'm gonna miss this when I graduate.
This year, right?
Yeah, this quarter. This quarter.
What's your experience with like moving to Washington C?
Yes, we have our next one.
Yeah,
Oh, I had Nisiri for 118C.
based off of the.
Oh, based on people I tutor, her vocab, the problem sets are gonna come back from 118A, like the problem sets, and those are like really tricky as well. There's midterms for 118C. Yeah.
Did you tutor over the summer or like?
Oh no, I didn't tutor over the summer, but I know she did teach 118B over the summer, like some summers ago. Yeah,
Because,
everything is, yeah, I know. I know. Oh, nice.
Yeah, these are just all the concepts for it.
Yeah, so I just email me and I said, oh.
You're like, you're like, gonna take.
Don't necessarily denote SP3 like configurations, but negative charges at stuff like that does.
Yeah, negative charges count as a lone pair of electrons, where it's not always shown on the exam, but you assume it's there, which can do resonance. But the positive charge here has no electrons there. It's an empty 3 orbital, which does not resonate. Right. Right. Where that carbon right there is sp2 hybridized. The carbons that are sp2 hybridized are carbocations like this, carb anions with a negative charge, and radicals, and double bonded carbons. Right.
So all of these are sp2 hybridized, planar, and fully conjugated with 2 pairs of electrons, which is an even pair, anti-aromatic. Nice. Yes. Oh, half and half.
Is it not completely conjugate?
Oh, no, it's not planar, because it's active.
Yeah, this is one of the oddball ones where this is the boat shaped one, the boat shape. So this is non-aromatic because it's non-planar.
Would we have just noticed only because it's an 8-member?
8-member ring, right?
So it'd be like 8-member, like 8 or more, would probably be like not planar.
Yeah, there are some cases where there are more like bigger rings in the weird annuline shape that are planar. And that's like a memorization thing.
That's the 4n plus 2.
The 4n plus 2 annuline thing, right, right. Where the most iconic non-planar things are this boat shape
thing and that weird thing with the pocket in the middle, but how you can avoid each other.
Oh, the one that you showed us earlier.
Yeah,
Okay.
right.
But Pascal says that is aromatic. So, but in this Kahoot, I put them as yeah.
What was Pascal's reasoning for that pin down?
He said that
He said it better into the boat trade.
no, he was talking about like which one are you guys talking about? Like
The one that was
one
like
you
that
just showed.
is from the.
Oh, this one right here?
Yeah.
Or yeah, that one is non-aromatic. That's not planar. But then he says this one is
Oh, the
aromatic.
one with
Oh, yeah.
the
The
trans hydrogens.
Yeah, the trans hydrogens. He says this one is aromatic, even though it's supposed to be non-aromatic, because the aromatic factor overpowers that thing. It's a driving factor for it to be planar. But it's supposed to be non-planar and non-aromatic. But he did show that the both thing there, the 8-membered ring, is non-planar.
And you
non-
like give a reasoning behind it, or you just say that one's aromatic? Or and.
Oh, yeah, he said aromatic is a driving factor for it to be planar, so it prefers to be planar, but it doesn't prefer to be planar in this case, because of steric agents here. Because those two are like so close to each other. But he said it prefers to be planar because it's aromatic, but the textbook says otherwise, and the other professors says otherwise.
The textbook mentioned that too as well.
Yeah,
I mean.
People are just like
on-
blitzed.
yeah. Maybe we can make it on it in the futures.
On an exam, like
lecture.
if you were said, non-aromatic, then you could probably get the points, so you can say the textbook says.
yeah. I would do that. Like if I would put non-aromatic on the test, and if they took points off, I would request regrade and say that.
That's my synthesis.
Mhm.
Yeah, only one of the lone pairs reacts. Oh, or conjugates. There are two lone pairs there, but only one of them does resonance. Right.
The other one is on the sp2 orbital. Right. So
For this structure here, whenever you have a carbonyl in the ring, always think about the resonance structure, where the carbons of the carbonyl always have a positive charge. Right? This double bond here does not count in the conjugated system. We always have to think of positive charges here, where there's only one pair, an odd pair, doing resonance with these carbocations there, which is aromatic.
Like, is this a question of like the way it is now?
yeah, the way it is now, yeah. Right. So in this case,
It is fully conjugated. It is all sp2, but it is not cyclic. It's not in the ring.
Why was this not bed?
all right. So, I think because it's like all flat, it's anti-aromatic. Like it's not able to bend because the geometry of this doesn't allow it to bend because everything is all flat in that case.
Oh,
Like the benzenes are both flat and it's just those two.
Just flat and forced to be there, right? It's not big enough to bend like the bolt. The bolt octagon thing is big enough to bend into the bolt shape, but this is not big enough to bend like that.
Oh yeah, I won't be able to host my office hours tonight because I'm going back to San Jose. So tonight I have to skip my office hours. Yeah. Right. So this nitrogen does have a lone pair of electrons, but it cannot resonate with the ring because that nitrogen there is already double bonded with the carbon. If it's already double bonded with the carbon, this lone pair there does not resonate. It's just 1, 2, 3 pairs, odd pairs, aromatic. If that wasn't there, then this can do resonance if there's a resonance available. Yeah. sp3 roadblock, blocking resonance, not fully conjugated. Non-aromatic. Okay, this is the last one, the last aromatic thing. Nice. Aromatic. Nice. Think about the first atom, very first atom directly attached to the benzene ring, and think about its partial charge. Is it partially negative, partially positive? EWG, because this carbon here is the atom directly attached to the benzene ring, which is triple bonded to the nitrogen. And it's partially positive because that nitrogen is more electronegative than that carbon, making that an EWG because it wants to gain electrons since it's positive. Nice. Oh shoot, I didn't go over this functional group. Oh my gosh. Let me just break the resonance structure of this on the board. Right, where this is the group, its resonance structure is gonna look like this. Right. This is the atom directly attached to the benzene ring right there. Yeah, positive charge, EWG.
good charge.
Yeah. Yeah, that's more towards the end of 118B, that functional group.
What was the thing that like you said was part of tautomerization?
Oh, enol.
Enol.
Enol, yeah. That's a beta unsaturated ketone or enone. Last 2-3 weeks of 118B, so don't worry about that right now. Yeah. Yes, nice.
Thank you.
Yeah, no problem. See ya.
We didn't sign in yet.
Oh yeah. Thanks.
So far, you're doing fine. All of the class over. But even the ones I don't like using them. Oh, it's been great. What the heck?
Nice. EDG. Thank you. You guys are able to identify these quickly now. Yeah, see ya. Nice. Yeah, yeah. Mhm. Right. So halogens are EWGs, but are they ortho paradirectors or meta directors? Ortho paradirector, right? This is the exception here. Even though they're EWGs, not meta directors, they are ortho para because of the resonance that they could do. Oh shoot. I don't think we can be over this. But SLGH. S is less electronegative than oxygen, so that makes S. Nice. Oh, yeah. So S is partial positive because it's less electronegative than oxygen, making it an EWG. Nice. Right. The oxygen is the one directly attached to the benzene ring. Some people might think it's an EWG because they see the carbonyl, the carbon double bond, but that's not the one directly attached to the ring. We always look at the one directly attached to the ring. Nice. And our group is EDG. It's a weak EWG. Any random R group. Isopropyl, methyl, ethyl, EDG. Yeah. Uh-huh. Oh, right. So think about like the sp3 orbitals on the sp3 carbons, right? Those sp3 orbitals have electrons on them, which just naturally donate electrons into the ring.
Because the ring is more stable.
Yeah, the ring is more stable, which allows the electrons to go towards that ring.
Oh.
Yeah, yeah. But that's good that you're asking like conceptual questions, like why that, because it could show up on the exam. Nice. So the atom directly attached to the ring is that carbonyl of the amide, which is partial positive, making it an EWG. Nice. Right. This one, I think it, yeah, like the extra negativity. Yeah. Right. So this NO2 group looks like this right here. NO2, but that atom, nitrogen, is positively charged, making it EWG.
I just keep thinking of it that like, oh, it's more electronegative, so then it would be the negative and then N is the partial positive and.
Yeah, that's another way to think about it as well. And since it's partial positive, it's EWG. So this atom here directly attached to the ring is this nitrogen, which is partial negative because it's attached to the carbon. And the nitrogen is more electronegative than the carbon. Nice. And that was it.
You should give out prizes.
Oh, give out prizes for Kahoot? Oh, that's a good idea. I should.
But
Like to motivate people to do well in the Kahoots.
Yeah.
Okay, I'll think of a prize, maybe snacks or candy or something. I don't know. Yeah. Uh-huh.
thank you.